So good morning again, everyone. Today I'll continue to talk about intermartensitic transitions. I'll go back from the beginning just quickly, what I briefly presented yesterday, but wasn't towards the end of the lecture. And then in the second half, we'll have a practice session on data fitting using the GIAN program. Now, we are talking about intermartensitic transitions, modulated states, and so on. And many of you are here working with Heusler's, and or will be working with Heusler-like materials, so that dealing with modulated states becomes very important. You have your X-ray machine here. You can take your data, and I've already seen some. The question is, of course, then these data have to be somehow reduced. And so I'll try to show you here, and there are experts better than me on this program who can also show you how things go on, and we'll see. Those who are more away from this topic can also follow. It is they'll come across it. They'll find the need for it somehow, using a refining technique, or whether when you see someone who's using a refining technique, at least you know what the person is doing. Okay, so it's important whether you're in the topic or not in the topic. Both ways, you'll benefit from it if we do a few examples on these things. Now, yesterday, while talking about intermartensitic transitions, okay, we just briefly talked about our austenite-martensite states. Now everybody's an expert on these in this audience, on what is austenite and what is martensite. Normally they're two different structures. And I try to simplify things, so I added another slide over here. This is a graphical representation. It's so you have basically an L10 structure, and if you repeat this L10 structure, you have a representation of the so-called NM equals S plus 1 relationship. Now NM, N stands for the number here in the beginning, and S stands for the number of satellites you observe. So when you do if you do an electron diffraction experiment, you'll get main spots and you'll get satellite spots. Or if you do an XRD experiment, you'll get a main peak and then you'll get the satellite peaks. It doesn't matter whether you're doing electron diffraction or X-ray diffraction. I mean, you get the same thing. Basically, you get intensities and satellites. Now, assuming that these here are the main spots that you observe, in the case when you have a modulation, then you get spots that are in the middle. You have 4 spots, so S plus 1 is then the 5M. If you have 6 spots, you have the 7M. And then you can have 9 spots, and that gives you the 10M. And this is the reason why they abandoned this 10M thing that was used for 5M in the past, because there are actually 10M modulations as well, but I mean, we won't go into those a lot. So this is the basic way of designating it, and what you see here is a 5M repetition and a 7M repetition. Of course, things are not that easy. When you really, when you have modulated state, you need the modulations. This is just a representation. There is no modulation there. So if you bring in the modulation, things look a little different. So this is a so-called, I don't know how to pronounce this, Zhadanov, or anyhow. He's come up with he's introduced sequences which are represented like this. So you'll come across these kinds of representations in some papers and things like that. So this would be 4 minus 3 repeated 2 times. Okay, so it's 1, 2, 3, 4, 1, 2, 3, and this whole thing repeated 2 times gives a designation like this. 5, 2, this is also a 7M modulated state. It can also be like this. You can have 1, 2, 3, 4, 5, and then 2, 5, and then 2 again. So 7M is a little tricky in that sense. If we go to the commensurate case of the 5M, we have this kind of representation where we have 3 and then 2, 3 and then 2. So as this number here gets larger, then you have other combinations coming up. So this is also just a representation. It does not treat the real case, although many people have tried it, including us at one time, to treat this as the real case. But it turns out that these structures, yes, they do exist, but their positions are not exactly the way they are shown over here, and you come up with so-called commensurate and incommensurate states. Now, the way to show a commensurate state or an incommensurate state, or we deal with so-called aperiodic crystal structures. They appear to be periodic, but it turns out that the periodicity of the crystal and the so-called modulation vector, they do not match. And so what we have a basis structure, which is the L10, and then these are moved around so that we have a we've given a periodic distortion, and thereby we get the so-called modulated crystal, which are represented by the lattice parameters ABC in 3 dimensions, and then you need the extra dimension of this Q vector, which would be the modulation, vector. So this I showed you in the previous case, where we have where we represent the satellite peaks between 2 spots. This is more a real case. It's not exactly real, but it shows you what you would see if you would do electron diffraction. You would get your main spots, and then in between there you have your satellite peaks. So you have satellite peaks, and you have modulated structures, and your whole periodicity is then described not in 3 dimensions, but in 4 dimensions. So you have your reciprocal lattice vectors plus your Q vector, right? If I say something wrong, let me know, okay? Anyhow, so let's go a bit further. There were some questions concerning this slide yesterday. Here again, we see some satellite peaks, okay? We have 1 spot here, 1 spot here, then we have 1, 2, 3, 4. What do we have here? 1, 2, 3, 4, 5. You see the problems now already coming out, what the real case is and what's not. Now, when you are incommensurate, then the spots don't seem to appear anymore at the positions that they're supposed to appear to. Or you have extra spots, or you have intensity problems. Now, this makes a mess of the whole thing. And nothing is easy anymore. Okay? And each is an individual case. So, people have taken diffractograms. So you see very nice X-ray data with all sorts of peaks coming out here and there. But then when it comes to the interpretation or to the fitting, then it is not straightforward. So this is where YANA comes in, actually, the program. People have developed a program to deal with these modulated phases to a certain extent by iterative methods. And with using these methods, we can play around with various parameters and try to match our inputs to the data. Let's look at these. These are also representative. These are also not what you would call the real case. So 5M. This is the easiest, perhaps, because in the 5M you do get this is a Danoff picture, the commensurate case. So you have 5 cells, let's say, and your modulation vector actually runs over 2 periods in these 5 cells. So that gives you a modulation of 2/5. Okay? 1. Now, you can have a 5M incommensurate case, and how do you represent this? So you have, this would be your 5 cells, but it turns out that the modulation vector doesn't end here, but it ends here. So you're already in trouble. Yeah? So how much more do I have to extend the periodicity so that I do get a match between the structure and the modulation? Turns out this is an example for the case of a 3 complete oscillations over a period of 7 vectors. So this is 3/7. Now, so you're going to ask me, well, what happened to the 5? You know, sort of thing like that. Well, it's gone. It's very washy between 5M incommensurate and when you go to the 7Ms, things like that. It becomes very difficult to distinguish what is really 5M and what is 7. It's a question of the modulation vector, how the modulation vector changes. And we extract the modulation vector from our refinement program, and then it delivers a value which we then have to play around with to understand what the periodicity is. Now, in the case of a 7M, let's see what's happened. This thing didn't finish here, it ended here. In the case of a 7M, it is not possible to construct a commensurate structure. It doesn't work. So in this case, for example, you have a periodicity over 10 cells. So it's like 3/10. So this is like 2/5. And this is like 3/10. Now, how do you know where you're going to start, what you're going to do? That is experience. So you look at your X-ray data, you try to figure out whether I could fit better to a 5M or better to a 7M. It turns out, by the way, when you're trying to fit to a 7M, it's not exactly a tetragonally modulated. You have monoclinic distortions you have to worry about. Like I said, these are only representative diagrams that give you an idea of the relationship between the structure and the modulation vector. So what did we have here? I didn't count. 1, 2, 3, 4, 5. We've got 6. 1, 2, 3, 4, 5, 6. Now what would that mean? That would mean 7M. Yeah? So it's 6 plus 1. We have something that looks like a 7M structure. But if you look at the intensities, this intensity is different from that one. The spots of vein intensities are different. The positions, they look very nice here. I mean, if you hadn't done any refinement or anything like that, you might have said just 7M commensurate. And I've got 6 spots, 7M commensurate, and finished. But it's not like that. So now, let's go to a bit of why we're doing all of this. Why do we want to know the structure? Well, we want to know the structures, especially of these functional materials, especially if we want to know what the relationship between the functionality and the structure is. So for that, we have to know the phase diagrams, how these structures evolve as a function of composition. in these things. I showed you this diagram yesterday a little bit, showing the various phase diagrams of the Oyster systems with gallium, indium, antimony, and tin, starting with gallium, indium, tin, and antimony. And as you see, the Martensitic transformation temperature slope that increases with, well, let's say increasing electron composition of the main group element. Tin has 5 S plus P electrons. Tin has 4 S plus P electrons, and antimony has 5. And these two have here 3. But each has its own slope, so to speak. So then we're here in all of these is the region where we have the functionalities of these materials, the magnetocaloric effects, shape memory, and stuff like that. Yes, we are here. We have, let's say, a single crystal. We're applying a magnetic field. We have a magnetic shape memory effect. Good. But in which temperature range can we use this? Can we reuse this in all temperature ranges? We know what the structure is at room temperature, but if we send this down to low temperature and reheat it, will we be able to use it again? Things like that. If we took this into space where temperatures are low, can we use magnetic shape memory effects? Do the structures prevail? So we have to know what's going on almost everywhere. Now, the way to understand the structure, structural analysis is not enough alone. Now, I have to do a temperature-dependent measurement. If I did X-rays, how am I going to do it fast enough? So I have to, and for a large quantity of samples, you have to do a temperature-dependent X-ray measurements covering with every 5 degrees or something like that, which is, of course, not possible. So instead, what do you do first? You do first more conventional measurements, like magnetization and resistivity. You try to see what you have in your magnetization. You try to see what you have in your resistivity, and then you do your X-ray measurements, and then you do your X-ray measurements at special positions, and then you try to iteratively understand which transitions are located. So to do this, of course, you need a whole lot of samples. So you make a whole lot of samples, first of all, in the ranges that you want to study. And then you look at your magnetization data. You measure the magnetization. That's the easiest thing to do, quick enough. And then you have a magnetization of all sorts of data. Now, this is done for nickel, manganese, gallium. I'm giving you this example because it's the most common of all. And we have here magnetization data that is taken in 50 Ørsted and in 5 Tesla in 2 different magnetic fields. One at very low magnetic fields, where you try to see the intrinsic ordering, whatever is in the sample, the magnetic ordering, and then you pump in the field and you measure in saturation to extract information on the magnetic moments and things. Now, look at any one. Let's start here. We have nickel 2, manganese, gallium. That's the stoichiometric one. Yeah? Nickel 2, manganese, gallium. It's 50, 25, 25, so it's somewhere around there. And we have our Martensitic transition here. We're calling it Martensitic transition because we know it is. Yeah? Otherwise, from the magnetization data, you wouldn't have known it. You had to do something else to understand that. And then when we do this in 5 Tesla, you see that in 5 Tesla, in these strong field regimes, in all cases, you always find a small thermal hysteresis there. That tells you that even in 5 Tesla, the transition is still there. Okay. So what do we have? We have temperatures. We have a temperature here, temperature here, temperature here. What are those? Those are Martensitic transition temperatures. Good. We can then place our Martensitic transition temperature lines, MS, MF, AS, AF. That's all okay. So here also. But then what happens? I have here let's say take this one. We have an MS here and an AF here. We've got this huge area over here where something is going on. We don't know what's going on from here, but something is going on. And likewise, we have that in many other things happening. So what is happening? This is the Austenite-Curie temperature, right? This steep one over here. And the steep one eventually gives way to the Martensite state, so that the steep one is no longer there. And then we have this part coming in at a slightly higher composition of manganese. And we have now here a Curie temperature that that is in the Martensite state, is in the L10 state. So these have a cubic to Martensite transition, which you can see in that temperature range, but here you cannot see that anymore. And we have this huge hysteresis going on over here, which does not have anything to do with the Martensitic transition. So that makes us, it gives us an idea. It tells us that, okay, if it's not a Martensitic transition, then it must be an Intermartensitic transition. So that's our starting point. Okay. So what do we do next? Next, the best conventional technique that you can use to understand such data is to measure the resistivity, because the resistivity measures the it depends on the scattering phenomena which is going on in there, the electron scattering. And if you have a change in structure, you're going to have a change in the scattering properties, and that will reveal in the data. And if you take the same samples and if you measure the resistance in a similar temperature range, what is it that you see? You find here something. You find here something everywhere. You find some hysteresis going on here and there. Don't let these bother you at the moment. We don't know at the moment what they are. I mean, those labelings are there as a result, but we don't have the results yet. Yeah. So what we have is we have various hysteresis. You come down with the resistivity. If something funny happens here, you go back up. It doesn't follow the same path. So just as in the magnetization, in the resistivity, we see all certain things. Now, the thing that you have to do over here is take the temperatures where you see these anomalies in the magnetization and take them in the resistance and try to correlate the temperatures, see if they correlate. Are they the same? Are we seeing the same things? So, and then what do? You do a series of X-ray measurements as a function of temperature. So these are all X-ray diffraction measurements of the same samples. Here on this sample, this was done on cooling. So what you see is you measure at 250 Kelvin. You see a structure that is related to the cubic structure, and you go down to 130 Kelvin, and you have something related to the Martensitic structure. But that's the only data you can take, because each of these data takes about 5 or 6 hours to take. Okay? The magnetization and the resistivity data are not like that. You're finished with the resistance and the magnetization data in 5 or 6 hours. But the magnetization and the resistance, of course, don't tell you what your structures are, if there are transitions going on. And these tell us that there are structural transitions going on, actually. If you look at the next sample, you find an austenite, and then you find some structures which is identified with the 5M. When you do the refinements of all of these, then it's identified with the 5M incommensurate structure. And then you go into cases where you have, at room temperature, it's already Martensite in this sample, for example, and then you go down, it's cooling down to 500 Kelvin, and then you have a 7M coming out, you have L10 sneaking out, and when you go back, you see a hysteresis. So at 200 Kelvin, there was no L10, but on going back at 220 Kelvin, you have the L10 stuck in there. So it's hysteresis, okay? And you have to go to a higher temperature before you can get rid of the L10 over there. So when you look at the, go back and look at the resistance data, for example, it's all iterative. Then you say, so what I see from my X-rays is, for example, for this sample, I am in the 7M structure. That's what it says. And then I go down in the temperature, and I come to a point where the X-ray data taken down here tells me that I have a 7M plus L10. And the resistance, the fact that it retraces, means that that structure remains stable. Goes back and forth. Nothing further changes. No, there's no new scattering mechanism. But then it will start changing up there somewhere. But what happens? This is the forward transformation of some intermartensitic transition going on, and the reverse transition is somewhere up further. We don't know. But you see that the resistance has decreased over here. And then you look at the consistency. Should the resistance decrease or increase? Well, L10 is a structure that is a little bit more symmetric than of higher symmetry than the modulated structure. So automatically what one would say is that if that is the case, then the scattering would be less, so that the resistance would be less. And things like that are consistent. And you can see that almost everywhere. In this case, for example, you have a fully closed group. So you've come from some I don't know whether it's properly labeled over here, maybe some 5M plus 7M state, and then you've gone down, and then the 5M has disappeared, so all around here is 7M, and when you go back up again, it remains 7M until you come to this point where the loop closes and you're back to your original state. That is one example. So these are well, this was basically a PhD work, the whole thing. It took quite a long time to get all these data, to analyze everything individually and so. And these are the X-ray data, and this is briefly sort of putting together, gathering on how we understand the X-ray magnetization and the resistance data. This is just a result of a refinement. So taking this example, we are here in an austenite state. So what you first do, you do your refinements. You see that, you're in an austenite state, and then this here is identified as the 5M incommensurate state. Okay, you have the fourfold splitting. So you think it should be somewhere around 5. That's your starting point. That's how you start doing your refinements. So and then you have your magnetization. What does this tell you? 130 Kelvin. 130 Kelvin is somewhere here. Okay, and that looks like a pure Martensite state. There is no hysteresis down here. And then you look at your resistivity. Your resistivity shows around 200 Kelvin, which is around here. Also a small hysteresis, which is associated with the Martensitic transition here. Okay. So now you have here, in this case, a transition from the austenite to a 5M Martensite, and it seems that nothing much else is happening at the lower temperatures. So then we look at something a little bit more complex. This here is this broad region that we observe in the magnetization, which is blown up over here. So there's considerable hysteresis over there. And the question is, of course, what will happen if we examine the structure when we go down in temperature in steps, as we have done over here. So at 293 Kelvin, you're at room temperature, and then you're cooling. It remains as a commensurate 5M state. Now, why do we say commensurate? Because of the analysis tells us that our Q vector is in the order of about 0.4. There's no other reason. It can be 0.405, it can be 0.406, it can be 0.4 4, exactly. So this business of modulation is really something more, or the incommensuracy is something more general rather than being the exception. So when you have a Q equal 4 and a 5m commensurate modulated state, that is just a number, and that is a special case of the incommensurate condition. So then we go down, and then 200 Kelvin. Where's 200 Kelvin? It's somewhere here. 250 Kelvin was somewhere around here. And you find eventually some kind of a 5m or 7m coming up, and an L10 coming up. Okay? L10 always comes up at lower temperatures. And if you correlate that with the resistivity, then you have this, you start identifying using the magnetization and the resistivity the various structures that you have at various places. So you have this thing coming down. So you have a hysteresis up here, you have a hysteresis down here. This is associated with the regular Martensitic transition, and this is associated with the Intermartensitic transition. So what is coming up is eventually more and more L10 at low temperatures as we go to more higher manganese concentrations. And this is just another example where everything is preformed in a similar manner. Here you have a characteristic temperature. Here you have a characteristic temperature. 200 and some odd things. And then you go over here and you try to find these, you try to find out what is happening around here. See, when you're coming down for 300 Kelvin, which is here, you've gone into some kind of an intermartensitic state, which is a 7m, let's say. You go all the way down, you start going back up. When you're all the way down, you have generated some L10, but it's not there. So then you go back up, and the L10 remains. So it was not there at 200 Kelvin when you were cooling the sample. It started coming out at 140, and it's not gone before you reach a much higher temperature. So doing all of this, then you come to a conclusion where you can start constructing a phase diagram. And then what do we learn from these phase diagrams? This is the martensite start temperature just shown over here. And these are representations that we had in the older days. We had L10, then we had a 7m coming in, and then we had the 5m's coming in as we, in all four systems, in gallium, tin, antimony, and so on. So it's always an L10, 7m, and then 5m. It seems to be in that direction. Now, earlier, when we first constructed these very early phase diagrams, we didn't know anything about refinement or anything. So we had to do things iteratively, looking in catalogs and trying to understand what the peaks were. There was no mention of commensuracy or incommensuracy. Everything was strictly 5nm, 7m, and whatnot. Intermartensitic transitions were not even known. They weren't even thought about. Now, this goes up to 7.8. Yeah, nickel manganese would be 8.5, way out there somewhere. So this is the region where we have all the functionalities, actually. What do we have? If we had nickel manganese, just pure nickel manganese way out there, that would be L10, okay, even at high temperatures. But it turns out that this L10 starts to disappear and other things start coming in. But the L10, when you construct these various phase diagrams, let's look here. We had, from the magnetization, resistivity, and the XRD, we see that we are here at high temperature above this line here. We are in the L21 state. And then we go down in temperature. We go down from an L21 to a 7m. Okay? There are no points over here because we couldn't measure them. We come over here where we have more points which we have measured, I think. So we go from L21 to a state which is, this is the forward, this is the reverse, 5m plus 7m plus L10. And then we go back up in the temperature. This remains in this area here until you cross this. You lose the L10, and the 5m and the 7m start coming out. And if you connect all these lines over here, you find that for the 7.5 system, this remains as a 5m, and the L10 never comes out. So, this is a phase diagram, good, but what do we understand from these phase diagrams? First, as far as the functionalities are concerned, if we have a shape memory alloy or some functionality in this region over here, and this is room temperature, if we go down and up, does the structure change? Do we introduce new strains? Is the functionality the same functionality? So these are things that have to be considered. Yeah. So this tells us whether the material is still usable when we go down to low temperatures. If we go down to low temperatures and sit at low temperatures, we're in different states. Our magnetic shape memory effect may no longer be there, or may have changed its characteristics. So, that's why we have to know what is going on all over here. In magnetocalorics, if we have cooling effects, warming effects, if we want to build some kind of cooling devices or warming devices at these temperatures, these have to be taken into account using these materials. Secondly, it gives us an important, it delivers an important result concerning what these structures are. What is a modulated structure, after all? We have this beautiful L10 over here. Why do we have to have this mess over here? Yeah? And it seems that the ground state is L10 anyhow, because the L10 state appears below certain temperatures, be it a mixture. So in all these Häuslers, the actual true ground state is the L10 state, meaning that these modulated states that appear between the L21 and the L10 have to be some kinds of adaptive phases, frustrated phases, so that it's like supercooling. You have to from the L21, the thing wants to go into an L10, but it's trapped. It cannot, so it builds these structures. It's like magnetic frustration. It's the magnetic frustration analog for a lattice, to a certain extent. Yeah, the structure is under heavy strains and things like that in these modulated states, and once it gets into the L10, it's happy, if it can get in there. So we understand, and from these kinds of measurements, and when we have established some kind of a phase diagram composed of several points, and extrapolating these values within reasonable limits, we can get a general picture of what is going on, and we can in fact infer that a ground state should always be L10, which is in agreement with theory as well. Theoreticians have calculated ground states of these things. They always find that the L10 state is a state of lowest energy with respect to the binding energy of these other states. So this is the end of the phase diagram story, and basically. This is all what I want to say concerning the intermartensitic transitions. And as this point on, I think we can get started with our YANA. I have two data. One simple data, which is a refinement of the L10 structure, and one is a little bit more complex, which is a refinement of the 7M. Okay? So, and we can go through that together. So when you click on your YANA icon or whatever you have, does everybody get this? So now we're going to go through some very basic principles. Much of them I don't know myself. I'll try to get you through some very basic aspects of these things. Now, the first thing that you have to do is you have to load your data. Okay? So you do that by going to File. It's very unintuitive, this program. Let me tell you from the beginning, there's nothing intuitive about it. It's very user-unfriendly, and it crashes, okay? But it gives you good results once you get to use it. So under Files, there's this, you go to the Structure, and from Structure, you go to New, okay? And then you click on New. Now you have to select your directory, which is also quite tricky here. On the left pane, you go to wherever your directory is, okay? So let's start with the Indium IN 4.9, okay? So find the file where your IN 4.9 is. When you have found your directory, if you double-click on your directory, your file will appear on the right window. Nothing will appear on the left window. It will appear on the right window. So at the end, you should be seeing something like this. Does everybody have this window? Yeah. We all have that window. Okay. Now, the way to load this data, I mean, you would normally double-click on it, but it doesn't work like that. This is a funny program. So you see this little arrow down here? So you have to click on that. And only after that do you click on OK. And now your data is loaded, and there's this window over here. It's free. It's free. It's been written by some people in the Czech Republic, in Prague, and they distribute it. Every year, twice a year, they have a YANA workshop. You can go there. It's free of charge. You just sit down and learn. You just have to pay for your accommodation. And meals are also free. Does everybody have this window now? Okay. Now, this window has various selections. We're working with powder data over here. You can work single crystal structures, whatever. We're in powder data, and we have various, the format of our data, you click here, that is various constant wavelength data. So we work with a constant wavelength, okay? Various CW formats. Is that okay? So then we go to next. Here we choose the format of our data. It's pananalytical XRDML. This depends on the kind of an instrument that you're using. And then we say next. Now we start. Okay, so this is what we assume, what we think is a tetragonal structure, right? So what this thing wants is cell parameters. Cell parameters are A, B, C, and the angles alpha, beta, gamma. So we have to give those in with spaces. I have chosen to start with, for example, cell parameters 3.8 space 3.8 space 7.0 and then 90, 90, 90. Now these are, you have to go in with some parameters. It doesn't have to be the exact. The more exact it is, the better will the refinement will be, because if you're too far from your parameters, then the iterations take too long and they're not accurate. So then, 3.8, 3.8, 7.8. Can you read? 3.8, 3.87, 90, 90, 90. So our cell is, this is how Jana wants the cell parameters, okay? It's a little bit unconventional, but this is how they want it. And then we'll convert that to our regular cell parameters afterwards. It's like double the A parameter or something like that. It's double the conventional C parameter. So then below that there is this thing called the target dimension. That is now 3 because this is not a modulated state and we're not looking for a modulation vector. In the next example that we're going to do later on, we're going to set this to 4 and give in an estimated modulation vector in there. But now we leave this as 3. So then we go to X-ray tubes. What kind of an X-ray tube have you used? So you click on X-ray tube. We use copper. So we put in copper, and the wavelengths for K alpha 1 and K alpha 2, they appear in these boxes down here. All right? So we go to next. Now there are some things that you just click because it's just the procedure. So this is the import wizard. So we've imported our data and now we say finish. After we say finish, we say OK. Do you want to accept the made changes? Yes. Yes? Does everybody have this? And then we say, yes, I would like to continue with the wizard. Now the old wizard is gone, the new wizard is coming. Yes? So then we continue with the wizard. We say, OK. What you do here is we just say run refine here just once. So it collects the data and does all sorts of stuff itself. But when we go to open the listing, we say no. And then we say finish here. Do you really want to close the refinement tool? Yes. Okay. Now, we come to a window which tells us that it's going to do a space group test. We have to give in the space group. From the lattice parameters that we've given in there, it estimates itself and tries to find itself what the space group could be. So we go here to next. We have this window, which we don't do anything with this. And then we go to next again. And then we have several options here. Okay? So now we have triclinic, monoclinic, all sorts of things over here, and we have tetragonal, tetragonal. And the space group that we want to test, and which is also testable with the program, is I4/MMM. So we choose the 4MMM, the symmetry, next, and then we have to choose the centering, which is then I. Okay? And then we say next. So, and then we come to a window which says select space group. Okay? We select I4 MMM. And then we say next. and then finish. And then you say yes. When you said yes, it does some refinement, and then you say open the listing, no. And then information, okay. This is a subprogram which takes us into the positioning of the atoms and things like that. We don't want to have anything to do with this at the moment, so we just say quit here. Now we're ready to do some refinements. These are all inputs. We're back at this window. So now we have here three main things that we're going to deal with. We have this, the input icon. We have here a refinement icon. These we don't deal with. And we have a refine icon here. When we press on refine, we'll get refine. And then we have a profile view over here, which you can click anytime. We can do that right now. Just double click on profile viewer, and you'll see the data that you have imported. And in the data that you have imported, you'll see your data plus another yellow line. Now to get a better contrast, this yellow is bad, so you go into options down here, and you choose, instead of this yellow, if you choose red, then you can see better the data that you're looking at. Okay? So this is what we have. And when we go into the refinement, the bottom data is the difference between the fitted and the measured quantities. So whenever you want to come out of this window, you just say quit. It doesn't quit the program, it just goes back here. Let's look at our EDT M50 file. Let's double click on this and see what we've done. So all the information that we have input in the beginning has gone in here. So the cell parameters are there as far as we have given it. As we refine it, these will change. If we look under symmetry, it has a I4 MMM symmetry. So this is the main file. There is no refinement done over here. These are our inputs. So we can just say OK or escape, whichever one. So now we want to refine things. And the way to start out with this, you go to the edit profile. This edit profile and profile viewer are going to be the icons that we will be using. So edit profile, you have your lattice parameters here, which you've given in, and you have these little boxes. When you click on those little boxes, it'll do the refinement for those particular values. This is the cell. Here in the radiation, you've chosen your wavelengths. They are here. There's nothing else we have to do here at the moment. When we look at profile, what is the profile? What do you think the profile of our X-rays are? Okay, they can be Gaussian, Lorentzian, pseudo-void. We usually choose a pseudo-void. A pseudo-void is a mixture of Gaussian and the Lorentzian. Okay, usually it's a good starting point. I mean, if you're not sure. And then you have various functions here related to your Gaussian and related to your Lorentzian. And then you can have various kinds of corrections which you may be needing. And then you have a diffractometer where you've measured if there is any deviation from the alignment of your X-ray machine. If the alignment is somehow off to a certain extent, you can go to corrections here, and you can kind of play around with these various shifts over here. But let's go to cell first, and let's just, for an example, check on the A. If you check on the A, since this is A and C, if you check on A, since A and B are equal, it's not necessary to check on B. You can or you don't have to. The angles will not be varying, so we'll just leave that as 90 degrees. Now from here on, it's a big game. You play. You can do it in various different fashions. We'll say OK to this. Do you want to rewrite change file? Yes. Now we go into refine and we say refine. We double click on refine. Yeah. There we go. And when you double click on refine, this does 10 cycles, and in the upper window you will see various parameters. And this one over here is one to follow. That has to go down and down, and if it's low, your R value, then you have, at one point you have a reasonable fit. Okay? So now that we refined it, we want to see what we have refined. So you go into your profile viewer, double click on that, and well, something has happened. You see here the differences between the fit and the data are quite large, so we have to do more things. A way of looking at any one of the data is that it's very funny. You know, in Windows you would select. You select also here, but you have to start from the bottom and go up. Yeah, like this. And then you have to click anywhere, and then it will enlarge. So like I said, it's not intuitive. And you see that it's tried to make some fits to these double lines, this K alpha 1 and K alpha 2. If you want to go back, you say shrink this one here. This takes you back to the old data. So it's a little bit of a practice of getting this, this green window and then clicking on it to see the thing. Anyhow, so then we go to quit. And then we go back to edit profile again. So you see already that the ABC parameters have changed. We allowed them to change. So now we have to go into the profile and adjust the shape of our peaks. So here, these are associated. These values are associated with the profile. Let's start with Ly, just alone, and then say OK, and then say yes, and then again we say refine. And now try to watch what is happening over here. You see this number is getting smaller and smaller all of a sudden. It's gone down to about 12. 12, 1240. Yeah? Okay. So now that we've done a refinement, let's check our profile viewer. You see now that this is pretty good already. This delta I relative, the difference, is between minus 0.1 and 0.1, which is, okay, acceptable. And if you enlarge any one of these peaks around here, you see that, well, the fits are not too bad, actually. Something's going on, anyhow. They're shifted a little bit in their positions, which means that maybe the zero of our instrument is not exactly zero. There are some shifts. So let's quit. Open our edit profile. Go to profile. And now we unclick the ly, sorry. And then we go into corrections, and let's see if we have any shift. Let's refine the shift. So we say OK, overwrite yes, and then we refine again. So what is happening to our 12? Oh, it's going down again. It went down to 12. It's not changing very, very much. And open the listing. No. We go into Profile Viewer. And for the moment, you see this is shifted back now. So maybe we can just leave it like this. Okay? Now there are many other things you can choose as parameters. You can choose the other Ly, Lz, G things. It'll just make the refinement a little bit better. But at some point, it can work the other way around with Yana. Suddenly, you lose all your good values and everything is a mess. Okay? Then you have to start all over again. You can't recover it. Now, this R value goes down and down and down. You just want to keep it going more down, but then it just goes up, and then you have to start all over again. So let's just leave this as it is at the moment. And if you look now into your directory, into the file, you'll see that there are a whole bunch of files that have been generated, including your own original file in there. So that's why you have to start with an individual directory whenever you're working with something, because there are going to be many files written. So each data requires its own subdirectory. So since this was an example, I don't want to go into any more detail in this. This is what you get. Okay. You can print these. You can save these in various formats. The formats are not that good, but there are ways of getting around those problems anyhow. If you want to save. You can save it as a PostScript, HBGL, all these funny things that you never use, but I mean, those are the only ones that are available. And then you have to convert them. It's kind of a mess. So let's say quit, finished. This is over with. So, and then now we'll do an example for a modulated state, which is requires the defining of modulation vectors and things. And so when I've shown you that, then it's a question of playing around with the program, sitting and just solving all sorts of examples. Now, in the Yana homepage, there is this thing called the cookbook. And in the cookbook, you have examples. The cookbook also includes the use of other programs, atoms and things, so that you locate the atom positions and things. What we're doing right now is a Lebesgue fitting. It's not a Rietveld refinement. You can also do a Rietveld refinement with this thing, but then things start getting more complex. I'll leave you to that, okay? But for most practical purposes, for our cases, these kind of fits are usually convenient. So now, we start over again with our new structure. We go into File, Structure, and New. So now you have to find the You have to find the file where you have your data. So the data is something x equals 15.1, 220 Kelvin. Yeah? Okay? So again, you have to press this button down here to be able to load the data. That's the most important button in GIAN. Okay? So you press on it and you say OK. Again, we go through the same procedure of importing the data. So we have various CW formats, constant wavelength formats. And then we go to next. We have Panalytical XRDML. And then we say next. Now we put in the cell parameters. Now as cell parameters, as a starting point, I have chosen 4.31 and then space 5.6, space 4.2, 90, 91, and 90. So you see here we give a monoclinic distortion. It's an orthorhombic cell. This is our step in how we follow the to get our modulated structure. Now, after giving in these values, our target dimension is now 4. So we have 4 dimensions. We're changing only one modulation vector. It's possible to change the others as well. So now, first modulation vector. How do we define it? We said it was, we're thinking it's 7m. So 7m is something around, what was it, 0.3 or something? Yeah? So the way to describe the modulation vector is by writing down 0, 0, and 3. This tells us the modulation vector is in a particular direction. 0, 0, 3 with spaces. Yes, yes, yes. 0 space, 0 space, 3. That's important. Okay? So again, we go to the X-ray tube and we choose copper. And we're finished with this window. We go to next. Okay? So, and then we go and say finish. We say OK. Do you want to make accept? Yes. And then you say again, OK. And we say run refine. So this runs something. Open listing, no. And then finish. Do you want to close the refinement tool? Yes. So now we're going to do a group test. Okay? Oh, it's going to do a group test. So we say next. Again, next. Now, the structure that we have is a P2/M, the space group. And then since it's modulated, it's got some extensions which it will find itself. So we have the 2/M symmetry. We're going to test that, choose that. So we say next. And the centering is P. Say next. And then we have here a selection, and we have this here, which is P2/M, is the one that we want. Okay? And then we say next. And then we say finish. Do you want to refine the profile once more? Yes, let's refine it and see what happens. Nothing happens. Open the listing. No. And then we come into this other subprogram which places atoms and things, but we say OK and then quit. We don't want to do anything with this. So now, as we did before, let's go into the EDT M50. We have here our input data. And the symmetry, you see we have a P2M, but since it's modulated, then we have this extension over here now. So we can say escape or close. And now we go into edit profile, as we did before. And what do we want to refine? We have the A, B, C, beta, let's say. I think we can do this all at once. And if we go into profile, let's choose our pseudo void again. And let's just say OK here. Let's not choose anything because we may be refining too many things at the same time and then it'll get too complicated. Let's just say OK. Do you want to rewrite the change files? Yes. And let's run a refinement. So our R factor is quite large for the moment. Open the listing, no. And we open the profile viewer, and we get things like this. So we have green lines and we have white lines. The whites are the main peaks and the greens are the modulated. The satellite peaks, sorry. Due to the satellite peaks. So okay, so let's go back to our edit profile. And then let's now go to profile and LY. Okay? We'll say OK, yes, and we'll run a refinement. Now you see this value, it's run down quite rapidly. Open the listings, no. We look at our profile viewer. Let's enlarge this area and see what's happened, like this. It's a mess. But okay. So this is what we have for the moment. Let's try to see if we can improve that. Let's go to edit profile. And let's now leave these, unclick these parameters. And in the profile, now we can, let's change LX, I don't know, GVG, I've just selected these. And let's see what happens. Yes, and we refine. Open the listing, no. And we go into profile viewer. Oh, it's a mess. You see? So what happened is maybe we refined too many parameters at the same time. But this is how you work with it. I tried this last night. In the second shot, I got everything very beautifully fit. So Depends on the day. Maybe yesterday was Monday. Maybe Mondays it works better. I don't know. So you'll have to play with it. So now that you know how to use this, and you can go into more sophisticated details of this program and look at other things as well. But this is the idea of the whole thing. And so now that all of you have the program and things, if you have use for it, then you know where to start from at least and how to proceed. You can play around with the two data that I have given you, and you can also, if you have more interest in this, then you can spend a lot of time with the cookbook and you can do lots of things. Okay? So, I think that's enough for programming for today. So are there any questions?
So the target dimension is like 3 or 4, or it depends, like do the value changes?
3 is when you don't have any modulation.
And modulation 4.
Modulation is 4.
These are the only two values that we can put in the target dimension.
For our purposes, yes. I mean, if you have modulations, different modulations in different directions, you can increase your dimensions, but it depends on what you are using it for. But usually the case is for the hoists, we've never used dimensions for more than 4.
How do we know about these modulations in that case?
Well, you have to have information. You have to get. I mean, if you have a material, you're doing it for the first time. It's a trial and error thing. Okay. Now we know for the hoisters that it's 4, so we're using 4. It's also a question of experience on how many data you have seen, how much data you have seen, and what it can be. And it's also a question of how much you have used the program itself. So there are no strict rules for that. You just have to try.
And in the after we executed 4 for the target dimension, we have put first vector as 003.
Yes.
So what was that based on?
Now in the case of 5M, you would select 004, I think. Yeah. That gives you the 003. That would give you that is the those are the coefficients of the ABC coefficients of your Q vector. Yeah. So the ABC coefficients.
Yeah. So all the parameters which we choose, it is based on like how we go around choosing all the parameters which we choose.
Yeah, I mean, again, I said it's a question of experience. For example, if you have a face-centered cubic lattice of a metal, what is the lattice parameter? It's 3.6. Okay, but is it 3.589 or the 3.624? That depends on the system of what you have, if it's nickel or it's cobalt or whatever. You know from your experience that for certain systems, the lattice parameters range in a certain value, okay? And this you learn in time, which should have which. If you have a BCC lattice, let's say it's about 2.8, okay? That's how you sort of begin. Now we had a Heusler. Heuslers have a lattice parameter, the cubic state of about 6. Because it's almost twice BCC, right? Each cell, so if you look at a parameter, so it's around 6. So these are guesses. You don't have to guess exactly. But the guess should be as good as possible because as the refinement progresses, it chooses certain ranges. And if it falls beyond a certain range, then it starts collapsing and things. Maybe I did that over here. If I gave him one of my lattice parameters as too far-fetched, then you don't get a good refinement. So it's all experience.
Or we can just determine from our XRD data.
You can look at your XRD data, and you can estimate something there by hand. Yes, it is also possible. Just if it's a simple structure. Yeah. So if you have a simple structure, then you could look at your XRD data, and if you know your Miller indices, you can guess what the lattice parameter may be.
Suppose we have an unknown compound, just like a XRD of the red soil, you can say that. So is it possible to refine by using this software?
It's always possible to refine if you know what's in your compound. I mean, if you have a mixture, then you have to sort of have a good knowledge of what is in that mixture to begin with.
See, the word is refined, so you know.
So you know what it is, and you refine. Yeah, that's
If you don't know what it is, then it is determined.
Even for multiple phases, it will be difficult.
No.
No. Actually, in these examples, I can show it to you here very quickly. It's, I mean, I wanted to get into that. For example, in our hoisters, we always have manganese oxide. You can't avoid it. You always have manganese oxide from sample preparation, exposure to air, and so on. So there is this one thing over here. If you say here, tools, and then phases, and then you say new phase. When you've done that, you say manually and OK. You go through the process with a new phase, and you do the whole thing again. But now when you have the new phase, well, you have the new phase and the old phase and whatnot. It's all this one sample, and it's been taken on the same spectrometer, so that the peak shapes and things like that, they remain the same for both systems. But you can refine the individual cell parameters. So working with mixed phases is not a problem. In fact, you have to in many cases, because you never have a pure sample. You have something in there, you have another peak coming out, and it's almost always the case that you have a manganese oxide coming out in these cases.
The modulation vector is actually alpha into A star plus beta into B star plus gamma into C star, right?
Yeah, that's right. Yeah.
Now, when you chose 0, 0, 3, that means alpha equals 0, beta equals 0, and gamma equals 3.
Yes, that's right.
But in the 7M case, the gamma was actually 3 by 7, that is 0.428.
Yes.
So why do you choose 3?
Oh, just a starting point.
But,
It was three by 7. 3 by 7, 0.4. We chose it. I mean, you can choose 4 as well. I mean, you're putting that into a refinement.
while doing the fitting, you were choosing LX, LY different times, but you didn't choose Q3. I mean, you didn't choose to change
That's why I crashed. That's why I didn't choose Q3. I started the program by refining parameters and shapes and things, and then suddenly I had this funny peak over there because I forgot about refining Q3. I should have refined Q3.
So at the next step, when I just only clicked Q3 and tried to refine it, it crashed. I mean, it just didn't take the.
Well, I mean,
You have to go back to the initial values.
then you have to start over again.
I unchecked all.
Let me give you. If you uncheck something, you have to change the value by hand to its original value as well.
Okay,
Yeah? Okay.
That's why. Okay.
You have to initialize the values, and Jana does not do that alone. So it's best to start from the beginning.
Okay. Now
Okay.
I understood. Thank you.